Okay, good evening, everyone. So, today we are going to discuss about electromagnetic induction and related factors for the generators and transformers. So, the previous section we have studied about like what is a magnetism is, like electromagnetism is. So, in an electromagnetic induction, it is our trying, what we are trying to do is to generate electricity. The main use is to generate electricity. So in electromagnetic induction, let's start with the topic. So, right, so in the electromagnetic induction, the first thing is what is this electromagnetic induction is. So electromagnetic induction means when there is a coil, let's say there is a coil, in another word you call it like a solenoid, a coil like this, and let's say there is a magnet, and the magnet can be moved in and out of the coil, like you can bring it inside the coil and outside the coil. So basically what we do is we move a magnetic field in and out of the coil like this, so that the magnet is going to create a change in magnetic fields. So what we create is a here change in magnetic field. This is very important, that it to be a change. If it is a constant magnetic field, the magnetic induction we won't be able to do. So when we creating a change in magnetic field or flux, we call it is going to be cut by the coil. So the coil is going to cut. As a result, the coil can generate an EMF, which generates an EMF. EMF is a voltage. So a wire or a conductor or coil, when it tries to generate an electricity due to a change of magnetic field, or when it experiencing a change in magnetic field, in simple word we call it when the conductor cuts through the magnetic field, the conductor or the coil is capable of generating electricity or voltage EMF. This phenomenon we call electromagnetic induction. Now, electromagnetic induction is we use mainly in generators, and in generators to do the electromagnetic induction we need uh, a similar arrangement to a motor like we discussed in the previous section, and the there are many different forms of generators. Like you already know, there's a simple version of generators which is you called dynamos. So the dynamo is also generate electricity when you're pedaling a foot cycle. So in electromagnetic induction, this process, if you want to generate more electricity, let's say this process, this is generating a more current, and then to decide the amount of current to increase, if you want to increase the EMF induced, then there are three factors to do. So induced EMF or current can be increased by, so there are two factors. The first thing, we can increase the number of turns of the coil. So we can have a coil with more number of turns. Increase number of turns of the coil. There's another thing we can do, that is, we can increase the strength of the magnetic field. So increase strength of magnetic field. And also we can increases the rate at which the magnet moves. In another word, we call increase rate at which or rate at magnetic field is cut by conductor or coil. So in this way also, you can increases the magnetic induction, the electromagnetic induction in the process. And then there is uh, a direction finding method for this. Now, when we're generating an electricity or current, it has a direction. So we can actually decide the direction by using Fleming's Fleming's right hand rule. Right hand rule. So according to the Fleming's right hand rule, so thumb shows the direction of the motion. Now in this case, you need to have a movement to the coil or the conductor. So it shows the direction of the motion. And the first finger shows, as usual, magnetic field direction. So that the induced current direction is given by second finger, induced current. So this is how we can use the Fleming's right hand rule. So Fleming's right hand rule will give you the current direction. This is what you're going to find from the Fleming's right hand rule. Now, let's see what are the structural parts in a simple AC generator. So, simple AC generator consists of these parts. Especially we have two magnetic poles, opposite magnetic poles, north and south, and it has a coil. It has a coil, and the coil is connected to a special connector, which is we called slip rings. Slip rings, like this. There are two rings are there. Right. Usually, one connection is connected to one ring, and the other connection is connected to the other ring, so that one ring is for the positive terminal, one ring is to the negative terminal. So which means two terminals are connected through two slip rings. And this is connected by carbon brushes. So they are the carbon brushes. And the carbon brushes are connected to output circuit. Some output circuit, this can be mainly a transformer most of the cases because we want to increase or decrease the voltage. Otherwise, this can be simply an output, some output circuit that we need to work with. So here is, these are the parts. We have carbon brushes, and then we have slip rings, slip rings, and then there is a coil here. Here's a coil. Usually this has many number of turns, and then there are magnets or magnetic poles. Right. So that we have a simple connection of a generator, and this is the output load where we take the output current, right? And in a generator, what actually happens is the same thing we explained in the coil. So in a generator, we need to have an external connection to rotate the coil. Like in a uh, power stations, we have many different ways to rotate uh, a generator coil, which is attached to actually a turbine. So normally, a turbine is something which is attached to the generator coil, like this. So normally, if in a hydropower station, we send a water flow to rotate this. In a steam powered power station, we send a steam to rotate this. In the wind power stations or wind turbines, we send the wind to rotate this. So somehow we let it rotate. As a result, the coil you can rotate. Once the coil rotates, it cuts through the magnetic field between them. So there is a magnetic field between north and south, like this. And that magnetic field is going to be cut by the coil. So when the magnetic field is cut by the coil can generate a current, OEMF, we call it. So this induced current and voltages, we simply bring it out from the slip ring to the carbon brushes, and we provide them into the output so that we can bring electricity from this method. Right. This is basically how you generate the electricity using an AC generator. There's another important thing we do with this. We actually use this one in transformers. So transformer is a very useful device in distribution of electricity. There are two types of transformers we have. We have step-up transformers and step-down transformers. A step-up transformer is a transformer which increases the voltage when you supply some amount of input alternating voltage. Step-down transformers, they decreases the voltage when you provide an alternating input voltage. In both cases, or any condition, the transformer only operates with alternating current or alternating voltage. If you can't provide an alternating current or voltage, transformer is unable to function because the structure of the transformer happens in that way. This is a simple structure of a transformer. So the transformer has two coils. We call them primary coil and secondary coil, like this. Primary coil and secondary coil. So the primary coil is connected to the alternating current input. Here's the primary coil for that. And then we have a secondary coil, which is we call the output. Secondary coil, which is connected to an output load. So that what we expecting this to do is when we supply an alternating current for this, that can generate a magnetic field within this iron core. This is the iron core. So what iron core does is it brings magnetic field lines between primary coil to the secondary coil. It's kind of channeling them from primary to the secondary coil. So that the primary coil to secondary coil, a magnetic field movement occurs, and the secondary coil cut this magnetic field and generates an EMF. So that is how you're supplying a large voltage or small voltage, we get another voltage from the secondary coil. Now we also mentioned that we need to have either higher voltage or lower voltage. And how we do that is by changing the number of turns in the secondary coil. So we can discuss this amount of voltage based on equation. So we usually write this one in different formats. So I will use one format like this. Number of turns in the secondary coil over number of turns in the primary coil equals to voltage provided to the secondary coil and voltage provided to the primary coil. This is the transformer's equation. Transform equation. And in the transform equation, what we do is to calculate either number of turns or the voltage. If you know the input voltage, you can calculate how much of output you can get. Or if you know the output, you can calculate how much of number of turns which can provide that. And the other thing is, in a transformer, there are so many heat losses occur, which means transformers usually lose heat as a heating effect in its resistance and many other options. So that if you're defining a transformer, let's say, thinking like there is no heat lost at 100% level, which means it is be called an ideal transformer. So that ideal transformer is a transformer which does not have any power or energy losses. So when the transformer does not have any power or energy losses, it is 100% efficient transformer. 100% efficient transformer. So that kind of a transformers are usually we don't find in the practical applications. Every transformer we are using is going to have some amount of heat losses, right? So this is all about the electromagnetic induction part, uh, which we normally discuss under this section. This lesson is also going to connect it to another lesson, which is you call the grid network, uh, and we will be discussing about grid network in the later session.